Hello there, chemistry minions.
It's MoNaCo.
And Mr. Milks, Unit 9.
Second video, Kinetics and Equilibrium. We got to know about what vocabulary is testable out there.
Yeah, page 4 and 5.
A bunch of terms.
Let's get to it.
First
Number
thing, kinetics. It's the rate of the reaction. So how much product turns into the reactant per unit time. Like
how fast?
Yeah, that's the simplest way to understand it. How quick a reaction goes.
Reaction. The rearrangement of atoms to form new compounds. Heat or light may be produced.
Right, so the actual moment the atoms rearrange from the products to the reactants.
Well, the reactants to the products. Let's do it that way.
Yeah, I was backwards.
That's all right.
A mechanism. Now, we don't go into the study the details of what mechanism is, but
no.
A mechanism is like that moment by moment, nanosecond by nanosecond, three-dimensional arrangement of atoms when the reactants are hitting each other and rearranging to make the products. How many steps go through there determine how fast the reaction goes.
Yeah, I think that it's a balanced chemical equation doesn't show you every step. It shows you the beginning and the end, and it misses a lot of the middle steps.
Like the nanoseconds that it takes for this atom to bump into that atom, or the arrangement that they have to hit each other
right.
in.
And a lot of times these reactions are three-step reactions.
Yeah.
Where the reactant's got to form this before then that can react back with the other thing, and we don't deal with that in a balanced chemical reaction.
And we don't.
But they exist.
You don't need to know any of that stuff. All you need to know is that the more steps in a reaction there are,
The slower
it's going to be.
There you go. Reaction rate.
How quickly the reaction occurs, time versus progress. So rusting of your bike chain is a very slow reaction rate because you might leave your bike out for a few days before it gets rusty in the rain.
Right, where combustion is usually a really fast reaction.
Right, you flick the Bic lighter and boom, it's burning instantly.
There you go.
Okay.
Collision theory, the theory that describes what it takes for a reaction to occur. It starts with a collision of the reactants. They literally have to come into physical contact with each other.
And this is a proper noun, collision theory. That's why it's capitalized, okay? So it describes two things that every reaction's got to do.
Well, the effective collision does, definitely. Here we go.
So here you are.
Keep moving. The effective collision is
a collision of reactants with enough energy and orientation to start a chemical reaction. If you think about it, reactant A and reactant B have to hit each other in the sweet spot with enough energy to become product AB actually stuck together.
right.
Atoms need energy in order to rearrange.
Right. Too slow, they don't make good contact. Too fast, they go past each other or bounce off.
Right. And the proper orientation is if the left side of A needs to connect with the right side of B, but they're not hitting on that angle, they're not going to react.
A lot like how the enzyme and the substrate got together in living environment, how it had to fit in like a puzzle.
Yeah, and
there's a spot where there's a reaction.
I just remembered another analogy. An effective collision is a lot like an effective handshake.
Okay.
Some people shake hands real weak-like, and you're like, Some people shake hands way too hard.
Yeah, trying too much.
Trying too hard. And then, here's another thing. My left hand can't shake your right hand if we're facing each other.
Right.
It's not the proper handshake.
It's not the proper
If you don't reach out in the right way to shake somebody's
right hand or left hand,
crossing the body and space in between the two bodies, it's not really.
That's a pretty good analogy. I like that. Did you just come up with that on top of your head right now?
Years ago.
Oh, okay. Catalyst, a substance that speeds up a chemical reaction, but it is not consumed by the reaction. Generally, it still exists as itself when the reaction's done.
And what this is like, it's like a traffic cop directing the parts of the atoms that are about to react to their active site. It's like, hey, buddy, back it up over here. So it like organizes the reactants to orient themselves properly so that the reaction speeds up.
Right. What it actually does is reduces the amount of energy it takes.
Because
it's like
you got an air traffic control guy going, right here, Mac, back it up over here. Or it's like a tool that you use to build a house. If I give you a hammer and nails and wood and blueprints, you could go build the frame of the house.
It'd take me a while.
Give the guy next to you the hammer, nails, compressor,
and
air gun. Yeah, nail gun, same blueprints, same wood. He's probably going to get his frame of his house up faster than you.
In this case, the nail gun would be the catalyst.
Or the hammer versus the nail gun.
Right.
I mean, you're not going to nail nails in without a hammer.
Right.
You need the tool. But anyways, thermodynamics. Study of entropy and enthalpy in chemical reactions. These are the two driving forces behind
Yes.
chemical reactions.
No, heat, enthalpy.
Heat and disorder.
There you go. The potential energy diagram is a graph showing us the difference between the potential energies of the reactants and the products. When we talk about potential energies here, we're talking about stored chemical energy in the bonds.
Right.
We won't get into that any more than that, but that's what we're talking about.
We're going to look at their progress on a graph. One of the things that you need to be able to read from your potential energy diagram is the heat of the reaction, which is the potential energy of the products, so that you ended with, minus the potential energy of the reactants, which you started with. This is not an equation you get on reference table T.
No, and it's very, very specific in the order because of the negative.
Right, and if you don't do it right, you will get the wrong sign
With
but
the right
value.
number. And you know how the Regents is. You know both answers are going to be present.
Mhm.
Yep, so we got to get that one right.
A forward reaction is, Mr. Milks,
Moving left to right, reactants to the products.
right, left side, right side.
Yep.
Reverse reactions, right side, left side. We're only going to see those when we get to equilibrium. Reaction coming back the other way.
Well, on those potential energy diagrams, you can go backwards.
What's the energy of the reverse reaction,
So you
right?
can do it.
Activation energy.
All right, this is going to be a big one.
Activation.
Both of these, the activation energy and the complex. So
Sure.
the activation energy is the energy I needed to get me from the reactants to this thing called the activated complex, and now we get to figure out what that happens to be.
The activated complex is that moment, the point where the reactants reach their maximum energy along the reactions pathway. So like in their progress to becoming the products, it's like the moment where everything's like jumbled up and rearranged, and it begins the formation of the products. This is the moment where the atoms have collided to the right orientation and the right amount of energy, and they're starting to break all the bonds that were in the reactants and form all the bonds that are in the products. So this femtosecond of reality is called the activated complex, where it's at its peak energy before it falls back down to its ending energy, and you can figure out the overall change.
We call it a complex because it is
really complex to what's going on.
Well, we're not going to get into what is actually going on at all. But while we have a
the
second,
mechanism,
we'll talk.
the steps of the mechanism are going on.
Yeah.
But we don't go into
Right,
those.
but that particular rearrangement of atoms is called this complex because it's neither the reactants or the products.
It's in flux.
Yeah, it is, and it's this complex thing. So that's that.
Yeah.
Equilibrium, a state where reactions are happening in both forward and reverse directions at the same time, simultaneously. Shown in equations with that double-headed arrow, either like this or above and below each other.
Meaning it's a two-way street, kid.
Yep, two-way street.
Whatever products become, it can also work backwards and go to the reactants. It's like it can fall apart just as easily as it was made.
Yep.
A physical equilibrium is where you've got a phase equilibrium. So like the melting of an ice cube is equal to the freezing of the ice cube. This is why at the freezing point of water, the temperature stays at 0.
Right, those flat lines and those curves that we did, those
and
heating
if you
cooling curves.
hold the temperature at 0, you're not going to create more ice cubes or water. It's just going to stay freezing and melting all at the same time. It's called a phase equilibrium. It happens at the melting and boiling points of substances.
Correct. Chemical equilibrium is more of a reaction equilibrium, and notice specifically the rate of the forward reaction is equal to the rate of the reverse reaction.
Right.
Nothing else has to be equal except for the rate.
These two reactants come together and synthesize a product. That product spontaneously falls apart again and goes backwards to make the two reactants that it formed from. Back and forth, back and forth. Game of ping pong.
Right.
With multiple ping pong balls at the same time.
There you go.
They're all in the air at once. Solution equilibrium is like dissolving solutions in solubility. So if I put a crystal of sodium chloride or copper sulfate pentahydrate into a beaker of water, and it's a saturated solution.
Right, so in other words, the solution itself is holding as much of that same stuff as it can already dissolve.
For every crystal that dissolves into the aqueous phase, a different chunk of aqueous solution, analyte, solute, crystallizes as well.
Right.
So it's like for every salt crystal that dissolves into the water,
2 ions come together and form a salt.
crystal.
And it's like a big cycle.
Starting around and around it goes.
Round and round it goes.
The
And
toughest thing about equilibriums to the human eye
is it looks like nothing's happening
It looks like nothing's going on.
because the concentrations of the reactants and the products stay exactly the same.
Constant.
That's that simultaneous thing.
So
So
we'll
it's-
get into more of that later. But let's move on.
All right, so the Le Chatelier's principle is going to be a big one towards the end. A reaction at equilibrium will shift towards the product or reactant side in order to regain said equilibrium.
I'm going to write something on the board. Mr. Milks will explain what it means.
Uh-oh, here we go. Teasing me because I don't even know what he's going to write. Here we go. Oh, yeah. AATT means away from what I add and towards what I take. That is going to help me figure out which way I shift.
Right. So if I add something, the reaction shifts away from it,
Right.
towards the other side of whatever you're
Right.
making.
And if I take something, let's say I create a product that I want. If I take
Remove it,
If I take some, the reaction's going to say, whoa, I need to make more.
and you're going to shift towards whatever you take. So AA and TT, very easy way.
To remember, well, to figure out which way am I actually going to shift once I tell you the shift, what the shift is.
Yep. So the stresses that we can put on equilibrium so that Le Chatelier's principle is observed, you can change concentrations like molarity. You can add or remove heat.
It'll be treated
Because-
just like a reactant or a product.
Because heat is a reactant or product in all reactions. Or pressure if we're talking about a gas. Because for gases, pressure is like concentration. The more you squeeze the particles together,
The closer
the more
they are.
likely they are to bump into each other, make a collision,
Collision theory.
effective collision, produce a product,
There we go.
shifting away from what you add towards what you take.
Nice.
Almost
So
done.
the equilibrium shift, I'm going to basically shift towards the reactant side of the product side
That's what
to
we're
relieve
saying.
that stress.
You can also say it to the right side or the left side
You can.
sometimes.
You
But either way.
Yep.
Entropy. This is that new word. It's a measure of the disorder in a system. Thermodynamics laws favor greater disorder, and it's shown by delta S in honors chemistry. If you don't use delta S in Regents anymore, but
We still need to know what it is.
yeah, sure. And the last one,
Ooh, enthalpy, delta H.
yep,
Equals the potential energy of the products minus the potential energy of the reactants. Specifically, again, that equation is not in your reference tables. You got to know it. These are found by looking into potential energy diagrams or Table H itself. So, guess what?
you got to know your testable vocabulary.
When you're ready, the vocab quiz is ready.
Not enough people were taking this vocab quiz as soon as they were done with their vocabulary
Seriously.
study.
And
like,
I had a lot of
Why
kids that were
bother?
like, Mister, I want to take the vocab quiz today. I'm like, great, it's right there. And they're like, well, I got to go study first. Well, isn't
Duh.
that what you're supposed to do
duh.
at
Study.
home? Like, study it.
And please don't waste your time. We're speeding up here.
Yeah, we got 2
Don't
weeks
waste your
when you
time
come
in
back,
school.
guys.
Do all your lectures and your pre-labs and stuff at home. That's what they're supposed to be for. We
Yeah.
don't put these on YouTube for
Yeah.
our own purpose.
I'm sure that even your CT teacher, if you're done with their work, you
My
say, hey,
pleasure.
listen, I got some chemistry work to do. Can I do that?
Yeah.
I'm sure they're going to say yes. See you guys.
Bye-bye.